Okay, take two. Cue clapping. Right, welcome back, everyone. Welcome back to our first monthly meeting since February 2020. That was the last one. And thank you, everybody, for making the effort to come here tonight. Now, please do take care and please follow our COVID protocols. Mark, I can hear people talking. Can you mute it? Oh, no, it's me. It's me talking. I can hear myself via Zoom. Oh, my God. Is that what I sound like? Okay. Okay. Well, okay. All right. Okay. Please do take care and use our COVID protocols. We've gone through a painstaking amount of work to check and double check and make sure we've got as much as we can covered. So there's COVID rules dotted around. There's hand sanitizer. Yeah. So please take care and please follow the rules. Now, welcome to those who are watching online on Zoom or on YouTube. Another first for the society. Unfortunately, I thought I'd be going global and everyone could see me, but the video is not working. So hello, everybody on YouTube or on Zoom. We normally leave the fire regulations out, but I can't find any. So if there's a fire, don't use the lifts and run down the stairs and meet outside. And that's about as far as I can go, really, because meet in Church Alley. Thank you. Meet in Church Alley. So yeah, that's just a precaution there. And also, can you make sure, if you haven't done so, please sign the book so that we know you're here. So if there is anything like that happens, then we can count the people. And also for COVID reasons, just in case. Okay. So I have here the minutes from the previous meeting, which was a Zoom meeting on the 15th of October, 2021. Now, in the past, we've read these out, but because it was the Zoom meeting, the council have read and approved the minutes of the meeting. And unless there's any objections, we're going to ratify it in that manner. So if anybody objects, please say so. Okay, thank you. So the minutes have been ratified, and if you need a copy, I do have a copy for you to look at, or if you want a version electronically, ask one of the council members and we'll get them emailed to you. Thank you. Okay, moving on. Mark, I can still hear myself in here. It's very distracting. Is that going to be like that all the time? All right. Okay. Sorry. Okay. Moving on. We move on to apologies for absence, and there are far too many names to read out tonight. So we will include them in the minutes of the meeting. And if anybody wants to see them next time around, they're welcome to do so. I'm going to move on to announcements. Okay. So I'm just going to go through a couple. We've got no raffle tonight, unfortunately, because of COVID. So, we can't do things like that just at the moment. Jim Stacey has some equipment for sale, including an EQ3 and a Coronado PST. So if anyone's interested in what he's got, then please see Mark at the break. Now, I would know, is Dave Galvin here? Okay. So there is some Hexil stuff that Dave Galvin wanted to cover. Are you able to cover that, Mark, or should we? Yeah, okay. So have you got some announcements to make? Yeah. Oh, okay. Okay. Well, let's move on, and we'll catch that later. Yeah. Okay. So, all right. Thanks. Okay. So there's been a few things happened at Pexel. If you're not aware, there's been windows broken. There's been a massive fly infestation and other things. Well, I won't. I'll let Dave explain that to you if we've got some time later. Okay. Do we have any new members here tonight, Chris? Yeah. So do I. Well, during the close down of the society, we've had loads and loads of people applying to join. In fact, we've got 70 people waiting to join. And the email to come tonight went out to all of them. Now, some of them might be listening online. We don't know. But I'll just reiterate, if you're watching on Zoom or on YouTube and you want to sign up to be a member, then you'll have to come to the next monthly meeting, please. Okay, so, and that's it. Has anybody got any announcements they want to make? Okay. Well, in that case, I'm going to hand it over to our guest speaker, who I'm sure you all recognize. And we've got part 3 of Fiat Lux, and this should be really good. So, Steve, I'm going to hand over to you. Do I need to give you this microphone thing? Okay. We'll do this better next time, Steve. I promise you. Is there a Fiat Lux 4? Okay, so the speaker's just starting up, and I believe the slides should be on Zoom and on YouTube as we go through the talk. So apologies you can't see me. I know you wanted to, but you'll have to make do with Steve's slides, which I'm sure is much better to look at than me.
Okay, is everything all right? Yes. Good evening, everybody. Could we have the lights down a little so that people can see the screen? Fantastic. Good evening to everybody live and good evening to everybody in Zoom land. So this is Fiat Lux 3. It is still coming through quite a few seconds after I'm speaking, Mark. Yeah, I can still hear it, yes. I can live with it if that's the best we can do, yeah? I'm just picking up good evening to everybody, and that was quite a few seconds ago, so if... I'm still hearing it all. Yep. Can we, is there anything we can do, or do I just talk loudly enough that... Let's just do a quick test. It seemed to be a few seconds delay, and now it's back again. Yeah, so I'm still hearing myself a few seconds afterwards. Okay, I'll just have to talk loudly enough and try and sort of ignore anything. Okay, let's try this again. Good evening, everybody. And good evening to everybody in Zoom land. So this is Fiat Lux 3, the third part of the trilogy. I gave you Fiat Lux 1 a little while ago. That's Fiat Lux in Hebrew and in Greek, if anybody's interested. But let me just remind you of Fiat Lux 1 was given to you in 2019. That's when I did some demonstrations and showed you that we can measure the speed of light, we can measure the wavelength of light, we can measure the wavelength of red light and blue light, and we also looked at other colors and polarization. So that was looking at the nature of light. Fiat Lux led to Fiat Lux II. And Fiat Lux II was looking at how we can use the nature of light to actually design optics such as telescopes. So Fiat Lux I was showing you, for instance, that vampires don't show up in reflections, which is why Fiat Lux II had the subtitle, The Vampire Strikes Back, being the second episode of the series. This is Fiat Lux III, where we're looking at a particular case study of a telescope that's going to be coming online in a couple of years' time, the Large Synoptic Survey Telescope, otherwise known as the LSST. And because it's the LSST and because this is episode 3 of the trilogy, I decided to call this episode 3, The Lost Jedi. So what are we actually going to be covering? We're going to be looking at sky surveys. Why should we survey the sky? What surveys have already been done? And basically, why do we need another one? And why do we need a special telescope to make this survey rather than make do with whatever we've got? What science is this survey going to deliver for us? And what technology do we need to actually give us that science? And then finally, I'll say a few words about the operation of the telescope and the data that it is going to be producing. So the question is, what's out there? It's a pretty fundamental question, what's out there? And you could say, well, surely all telescopes answer that question, or at least try to. Well, no, not really. Most telescopes actually look at objects we already know about. In other words, surveys have been done telling us what's in the sky, and then detailed telescopes such as the large aperture telescopes being built at the moment, or the Hubble Space Telescope, or ultimately the James Webb Space Telescope, will go and look at some of those objects that have been surveyed. Surveys down to a certain limiting magnitude have been carried out for quite a few decades. For instance, the Palomar Observatory survey in the 1940s and 50s used the 48-inch Schmidt camera located alongside the 200-inch Hale telescope, the 5-meter Hale telescope, Mount Palomar. And that was followed up by another Palomar survey some decades later, using more sensitive photographic plates to get a slightly better limiting magnitude. But essentially, it was survey the sky, try and take a picture of everything, and when you've done the whole sky, stop. And clearly, it's taken quite a few years just to survey the sky once. Now, you can tell from here, the clue is in the title. The next survey was the Digital Sky Survey, the Sloan Digital Sky Survey. And so clearly we've moved on from photographic plates to CCD cameras. And here a couple of telescopes, 2-meter class telescopes, took something of order 1 million images to survey the entire sky. And more recently, but overlapping in timescale, was Pan-STARRS, the Panoramic Survey Telescope System. Again, a pair of telescopes surveying essentially all of the sky. So what we're talking about here is the next generation of survey. Don't take the dates too seriously. It says here 2022 to 2032. It will be a 10-year project. Whether it will start next year or not, a certain pandemic has got in the way, and perhaps that's going to be put back by a year or so. So we can ask ourselves, why do we need another survey? What was wrong with the surveys we've already got? Well, if we think about the number of objects that are capable of being observed in a survey as a function of time, the original Palomar survey started down here somewhere at about 100 million objects. That might sound like a lot, but what we really want to get to is that gray line on the top. That gray line has been put somewhat arbitrarily there, as it's roughly speaking 100 billion stars in the Milky Way, maybe a few more, and there are something like hundreds of billions of galaxies in the universe. So if we want to look at all the stars and all the galaxies, we really need to be able to survey not just millions of objects, but many billions of objects. So that's the holy grail, the gray line. Palomar started down here, the second Palomar survey. And if we look at Sloan, that did the Digital Sky Survey did a little bit better, but only by an order of 3 or 4 or so. And Pan-STARRS has done a little bit better, but we're still a long way short of the gray line. The idea of the LSST project is that it will get us up to about there, not quite touching the gray line, but a significant fraction of all the stars in the Milky Way, a significant fraction of all the galaxies in the observable universe will be within the range of this particular project. Clearly, it must have started a while ago if it's coming online in another year or two. So it started a while ago and we are somewhere close to that red line. And hopefully that means that the project will be kicking off in another year or two. So the mantra of the Large Synoptic Survey Telescope is wide, fast, and deep. Why can't an existing telescope simply be repurposed for the job? Well, if we want to survey the entire sky, we must have at least 3 basic characteristics. We must have a wide field of view. Otherwise, it will take us years to survey the sky. It must be fast in the sense of optically fast in order to keep the exposures nice and short. And it must be deep. We must be able to see very faint objects. If we can't see faint objects, we're not going to survey anything that we could survey with previous projects. So we can do a little bit of horse trading between how wide a field of view do we want to cover with each exposure, how fast should the optics be, and how deep do we want to go in order to get the science that we want to do. A little bit of horse trading between these 3, but if you want the best survey instrument, it needs to excel at all of these 3 characteristics. And just to make sure everybody is clear, what do we mean by fast optics? Perhaps you already know this, but if we look at the focal ratio, the ratio of a focal length to the diameter of a lens or mirror, that F number tells us how fast the optics are. If the F number is low, that means we have very bright images, and so we can use relatively short exposures, or in the days of photography, we would say fast shutter speeds. With a low F number, we can use fast shutter speeds. So low F numbers, low values of focal length over diameter, or if you like, large diameters for a given focal length, then low F numbers mean that we have short exposures, which means we get a lot more done in a given time interval. So what we're after is small F numbers. And if we just take an example here, just hypothetically, if we had an object which we wanted to image, and we could do that with a 1-minute exposure, if our optics were f2, for instance, then if our optics were f2.8, we would have only half as much light coming into the optical system. So we would need to expose for twice as long. And similarly for f4, f5.6, f8, etc. They conventionally go up in factors of square root of 2 on the diameter, because that effectively halves or doubles the area of the objective. And for those of you who dabbled with astrophotography, you know the best thing you can do is to get a lens with an F number of 2 or 2.8 or 4 or something like that to give you plenty of light coming in to keep your exposures short. But if you ask yourself, well, what is the Hubble Space Telescope? Couldn't we use that? Is that not fast enough to do a survey? Well, if you think of the Hubble Space Telescope, the diameter of the mirror is 2.4 meters, and the focal length is nominally 57 meters, which means its F number is actually close to 22. It is no way could you call it a fast instrument, fast optically. So although the Hubble has fantastic resolution, if you wanted to survey the entire sky at f22, it would take you 100 years or more to do that. So the Hubble Space Telescope, fantastic though it is not the right instrument to do surveys. Well, you say, okay, if we want it to be fast, why don't we go with something with a much bigger mirror? Why don't we use the European Extremely Large Telescope coming online shortly? It's got a 40-meter diameter mirror. Surely that's fast enough for the job. Well, no, it's not the size of the mirror, it's the F number, it's the focal length divided by the mirror size. The mirror might be 40 meters across, but the focal length of the EELT, something of order 750 meters, 3/4 of a kilometer. And so the focal ratio of the EELT is about f16. So again, nowhere near enough for a survey instrument. We want wide and fast and deep. And if you use your digital SLR with a wide angle lens, you certainly get a nice wide chunk of sky, but it's not particularly fast and it's certainly not deep enough. DSLR with a telephoto lens, well, you might be able to go quite deep. With a telephoto lens, you can certainly photograph a quasar that's 25 billion light years away. I know because I tried that as a lockdown project, and yes, it works. You can do that. You can certainly image galaxies that are receding from us much faster than the speed of light. You can do that with a telephoto lens, but you don't have the wide angle and you don't have the fast optics. And we've just seen that Hubble Space Telescope and the ELT, for instance, they can definitely get the depth. They can definitely see very faint objects, but they aren't wide angle and they aren't particularly fast in the sense of keeping the exposure short. The Hubble Deep Field, for instance, was a 1 million second exposure. We can't afford to do long exposures if we want to survey the sky. So that's why the Large Synoptic Survey Telescope came into being. It is wide angle, it is fast, and it can go deep. Deep in this context means magnitudes much fainter than the sort of things that have been surveyed up to this point. Hence the mantra of the LSST project is wide, fast, and deep. And this is an indication of what it looks like. It's almost finished in the sense that a lot of the construction is already done. It's not all complete yet, so this is still an artist's impression, as it were, a little movie of what it will look like. It is a very large mirror for a given focal length, and hence it doesn't look like a conventional telescope, which tends to be, generally speaking, much longer than they are wide in diameter. One of the key aspects of the LSST is because it's wide and fast and deep, it can survey the sky in 3 nights. Remember, the Palomar survey or the Sloan survey or Pan-STARRS took years to map the sky. In the case of Palomar, it took about 10 years to survey the sky once. The LSST will survey the sky that it can see from a given location in 3 nights. In other words, it can map 1/3 of the sky that it can see every night that it's in operation. And because it can do the sky every 3 nights, that means over a period of years, it will revisit the same patch of sky multiple times. It is not just taking a snapshot. It's taking a movie of the sky. It's imaging, and then it will come back possibly days, possibly weeks later, and take another image, and then another, and then another. And virtually the entire sky is going to be imaged hundreds, if not thousands of times. So it's not just a snapshot of what was the brightness and position of that star at this particular date. It's what the brightness and position and color of that star is as a function of time over a 10-year period. Quite a different philosophy to other surveys. So the LSST is not only going to be comprehensive in terms of the number of objects that it's going to be looking at. Remember, tens of billions of stars and galaxies are going to be surveyed. The fact that this is done over a period of time and these objects will be looked at many times during the 10-year cycle is what makes the LSST unique as a project. So what are we hoping to learn from the LSST? Well, it should give us information about objects within the solar system and stars within the Milky Way and galaxies in the universe. In other words, essentially all scales of astronomy that we're generally interested in. What's going on inside the solar system, what's going on inside the galaxy, what's going on outside the galaxy. And in order to do that, they needed to develop a novel design of telescope, a novel design of camera, and data processing capabilities, which I'll mention at the end of the talk, which are truly staggering. It will generate by far the largest catalogue of astronomical objects that has ever been compiled. Even in a few nights, it will have compiled a catalogue bigger than every other survey up to that point over the past century or so. And it is hoped that the catalogue of everything we learn from doing this survey will act as a catalyst for either people data mining the information obtained in the catalogue, or it'll point the way for other telescopes to go and visit interesting objects that have been found by the survey. So the principal scientific aims, I'm not going to spend too long on the details because it is an enormous range that it is trying to deal with. Just very briefly, it's going to look at the solar system and effectively take an inventory of what is in the solar system and try and clarify how the solar system came to be. And that will hopefully help us with our understanding of how exoplanets move around other star systems. It's not going to just find thousands of asteroids and trans-Neptunian objects, it's probably going to find millions of them. Outside the solar system, we have the Milky Way, and we're going to be looking at stars within the Milky Way, determining the position of stars in the Milky Way and determining the Milky Way's evolution and finding properties of various stars. Some of you might say, well, isn't that what Gaia is doing? Gaia is a spacecraft which is mapping the positions of stars within our Milky Way to try and give us a better idea of how the Milky Way is put together. Well, yes, the LSST is going to be complementary to Gaia because the LSST will go deeper. In other words, it will go to fainter stars by quite a few magnitudes, which means effectively LSST is going to be exploring a volume which is much larger than the volume that can be explored by Gaia. Gaia has a magnitude limit. LSST will go beyond that limit and hence will be looking at stars beyond Gaia's capability. So in a sense, they are complementary. Gaia has fantastic resolution for positions of stars. LSST will be able to see fainter. In addition, there will be a mapping of some 20 billion galaxies. This is estimated, knowing the characteristics of the telescope and having some idea of how the observable universe is put together. It's been calculated that we can expect some 20 billion galaxies to be catalogued by the LSST. And in the process, we get a better idea of galaxy evolution, galaxy mergers, galaxy collisions because of the numbers that are being looked at. There's also the question of dark matter. The LSST is going to be imaging galaxies and stars. If we think just of galaxies for the moment, then we can think of galaxies and galaxy clusters. Gravitational lensing, the light will be bent by these galaxies and galaxy clusters, and the LSST will be able to determine the distribution of dark matter, where it is in the universe. We know it's out there. We're not too sure exactly where it is. So part of the LSST's remit is to try and map out where the dark matter is. Even though we can't see the dark matter, we can see the effect it has on the light from more distant galaxies because of this effect called gravitational lensing. Similarly, dark energy. Dark energy appears to be out there, and dark energy appears to be responsible for ripping the universe apart and accelerating the expansion of the universe. And the LSST will try and get some headway into understanding dark energy by looking, for instance, at supernova. Now, a supernova might only go off once in 100 years in a given galaxy. But if you're cataloging 20 billion galaxies, that means you're not going to find one or two supernova every night. You will probably find thousands of supernova every night for the entire 10 years of the project. So up till now, we know of a few thousand supernova that have been found by all the telescopes that have ever existed. But it's expected that the LSST will actually be able to image a few million supernova in its lifetime. So the catalog of supernova is going to go up enormously. In a single exposure, and a single exposure for the LSST means 15 seconds. That's what it's going to be doing. It's not going to be taking long exposures like the Hubble Deep Field. It's going to be taking lots of short exposures of 15 seconds apiece. And in a single exposure, it is expected that that single 15-second exposure will catch probably 5,000 moving objects. In addition to all of the stars, in addition to all of the galaxies that are within its field of view, it will catch perhaps 5,000 moving objects. Some of them might be asteroids, some of them might be trans-Neptunian objects. Over the period of the survey, it is expected that it will catch millions of asteroids and objects in the solar system. Yes, we already know about some of them. We already know about the bigger ones, but it's the smaller ones you have to watch out for. Something that's many kilometers in size, we might be able to track, but if one gets through that's a little bit smaller, that could be bad news for us. We know that there are lots of objects in Earth crossing we have all sorts of things going on beyond Neptune, even before we get to the Oort cloud. And some of these objects out there are in extremely eccentric elliptical orbits, and perhaps out there people have postulated is Planet 9. If Planet 9 exists, the LST will almost certainly find it with something like a 99.99% probability. If it's there, the LST will find it. So we know that there are a few objects out there that are bright enough to be seen, but we are sure that there are many thousands of objects out there that have not yet been picked up because we need a deep survey to find them. And that's what the LSST is going to be delivering. Within the Milky Way itself, that's always a little bit of a problem, trying to work out what the shape of an object is if you're living inside that object. So trying to figure out what is the structure of the Milky Way is surprisingly difficult. It's arguably easier to figure out the structure of other galaxies that are millions of light years away compared to the structure of our own Milky Way, simply because we're on the inside looking out. So it's only recently that we've actually got a reasonably good idea of what the spiral arm structure of our Milky Way is, the size of the bar in the middle, and the fact that our Milky Way has 4 spiral arms. That's where we live, just there on the Orion spur of one of the arms. A single exposure of a given survey area, in other words, taken over 3 nights, if we think about a 3-night set of exposures mapping the sky that we can see from a given point on the Earth's surface, that should effectively explore a volume. If you think of it as a 3-dimensional volume that's being imaged, that volume will be some 10 times larger than all previous surveys. In 3 nights, it will survey more than has been surveyed ever before. And by the time you get a 10-year survey and you start adding together all these images, co-adding and getting fainter and fainter and fainter objects coming in, then you will effectively have mapped a volume that is some 1,000 times larger. So again, that's why it's complementary to Gaia. Gaia is doing a fantastic job at finding star positions and star velocities, giving us information about what is going on with the Milky Way. But LSST will be able to effectively see inside a volume which is 1,000 times larger. In other words, Gaia is rather local compared to the huge volume that LSST will be able to explore. As a side issue, and it's essentially a side issue for Gaia as well as a side issue for LSST, one of the spin-offs that's not really one of the aims of the project, but one of the spin-offs is the fact that we're bound to find some new exoplanets as well. Remember, an exoplanet might be found if it happens to drift in front of a star and make the star's brightness change. So the chances of that happening aren't particularly high, but if you are surveying 10 billion stars, then it will actually find quite a few exoplanets, as it were, by accident. Simply by monitoring the starlight from billions of stars, you will find lots of exoplanets in the process. And that is probably true of Gaia as well for the more nearby stars. If one of the stars happens to be in the Magellanic Clouds, then that will probably end up being the first confirmation of an exoplanet in another galaxy. You might have heard recently about some X-ray measurements of something that might be an exoplanet in a more distant galaxy, but seeing something happen once doesn't convince you it's an exoplanet until you can get some idea of the periodicity. And it's thought that this planet won't eclipse the star again for perhaps another 20 or 30 years. So the confirmation of that tentative result will be a while coming. In the meantime, it is probable that LSST will find exoplanets in other galaxies. Interaction between galaxies is something, of course, we've known about for a while. It is not an uncommon event. Now that we've got the Hubble Space Telescope and we can see lots of different galaxies imaged in wonderful resolution, we find that a lot of these galaxies are not isolated, but are interacting with neighbors, or there are signs that they have interacted with some of their neighbors. This particular galaxy, M63, you may look at this and say, well, that looks like a rather isolated galaxy. It's a rather nice spiral. There's, of course, a few stars in the foreground from our own Milky Way. But on the whole, that looks like a rather isolated galaxy. If we take the color out and invert it to make it easier to see what's going on, so change black to white, and bump up the contrast, we can see that is not an isolated galaxy. That quite definitely has these tidal tails that indicate that it's been disrupted, probably by a near passage or possibly even a collision with another galaxy in the past. And the more we look, the more we find this sort of thing. Sometimes these tidal tails are quite faint. It is thought that the Milky Way has a similar arc, indicating that the Milky Way has interacted with other galaxies in its history. That is itself not a surprise, but if you monitor what these arcs look like, you can start to reconstruct what those interactions must have been like. And in this particular case, if we do the same again, invert it and bump up the contrast, you can see enormous tidal tails, which are sometimes bigger than the actual galaxies themselves, that indicate that there has been gravitational disruption by close passage of another neighbor, perhaps of a comparable size. This is thought to be the main process by which galaxies grow. Is after they are originally formed, they grow from eating other galaxies, by interacting, by colliding, by merging, in much the same way that the Milky Way galaxy will merge with the Andromeda galaxy in a few billion years and produce a rather large megagalaxy in the process. If we look at lots of galaxies, not all of them will be interacting, but if we see what's going on with billions of galaxies, we'll get a much better idea of these interactions. But the really big question is that if 5% of the universe is the matter that we understand, if we, as in you, me, Earth, Sun, all the stars in the Milky Way, all of the galaxies that we can see, if all of that is only 5% of the universe, then we have to really have a better job of understanding what the other 95% is. 27% of the universe is dark matter. We know it's out there. There's lots of evidence that dark matter exists, from looking at clusters of galaxies, by looking at galaxy rotations, by looking at gravitational lensing. Lots of evidence that it's out there, but we don't know exactly what it is, and we don't know exactly where it is. How is it distributed throughout the universe? The other 68% is even more mysterious, the dark energy that is making the expansion of the universe accelerate and effectively ripping the universe apart. We don't have a clue what it is, and we need to get a better angle on this, on both of these. If 95% of the universe is in this so-called dark sector, it's either dark matter or dark energy. If that accounts for 95% of what's out there, we really ought to do a better job of understanding what it is, rather than just concentrate on the 5%, which is the prettiest bit, the bit where the stars are giving us light. So we think the universe looks like this. We can't measure, we can't see dark matter. We can see the effect of dark matter, but we can't see it. But we think the dark matter is out there according to our simulations, and that's the best we can do at the moment. Simulations tell us that the universe is full of this dark web, this web structure with filaments and voids, and there are strands of dark matter linking together these nodes, which are where the superclusters and clusters and individual galaxies are forming. So here the yellowish stuff is the stuff that we can see, and it's inferred that we have this dark matter web in the background. But how can we tell if that particular simulation is right unless we can do some measurements to see what's actually out there? Maybe the dark matter is uniformly distributed, maybe it's more blotchy. This is simply an artist's impression of our lack of knowledge of how dark matter is distributed, either locally within the Milky Way or within any system of galaxies. One of the ways that it can measure dark matter, or at least infer the existence of dark matter, is to look at this gravitational lensing. Galaxies will be distorting the light from more distant galaxies, and if dark matter is added to the mix, the distortion is even larger. So if we can measure the distortion that we see due to various galaxies that are out there, we can start to piece together what dark matter is where and how it's distributed through space. In other words, does it follow the sort of filament and web-like structure that the simulations would have us believe? Similarly, when it comes to understanding dark energy, if we can understand where the dark matter is and we can get a handle on how that has changed, because if we look at different distances, we're looking back in time, if we can see how the dark matter of the universe has changed with time, that'll give us an idea of what dark energy is doing, because the dark energy will influence the dark matter. And again, here the red indicates what we think the dark matter web will look like, but we can't see that. But even though we can't see it, we can see galaxies, and the galaxies will be distorted slightly by the fact that dark matter will distort light. Again, gravitational lensing. Any light that travels through a dark matter area will be bent, perhaps only slightly, but even if it's only a very small effect, if you can see that small effect, not on a dozen galaxies or 100 galaxies or 1,000,000 galaxies, if you can add up that small effect that you can see over many billions of galaxies or tens of billions of galaxies, then we have a chance of saying, although individually we can't tell what's going on, but if we look at enough galaxies, we can infer what the web of dark matter must be that's producing that particular arrangement of galaxies that we can see. So that's the idea, using visible light to tell us what the dark matter is actually up to. So how are we going to actually deliver on this? This is the science we want to do. Excuse me a second while I try and take a sip of water without touching the microphone. So we're going to need a very special telescope. It's going to have a unique optical design. It's going to have the world's largest detector to give us the field of view that we need. And it's going to have an astounding observatory site. We can't place this somewhere where we're not going to get fantastic clear skies. As I think you're probably aware, the best sites in the world are either on the top of a volcano like Hawaii, or on volcanoes in the Canary Islands, La Palma and Tenerife, or in the Atacama Desert of Chile. And so these sites were considered, and it was decided that the LSST was going to be sited in Chile. That was decided a few years back. So there. That looks like it might be it, but no, that's not it. That is Gemini South. There's Gemini North and Gemini South, and the LSST is effectively on the next mountain along from Gemini South. So from the LSST site, when you look across the mountains, you see Gemini in the distance there. So they took the next mountain, blew the top off it, and then got a whole load of engineers in to go around saying, oh, I don't like the look of that. Yeah, okay. Oh, no, which cowboy did that then? And then they started building it a few years back. That is not bang up to date. That's still a little bit out of date. They are getting on nicely with the structure of the building and the telescope itself. That's an artist's impression of what it will look like when it's finished. A little telescope on the side, which will be surveying the state of the sky in terms of the seeing conditions. Inside will be the telescope itself and various support laboratories, such as, for instance, re-illuminizing the mirror whenever it gets dirty, whenever that's needed. That just gives you an idea of what the telescope looks like in its turret. The optical design is very curious. We want the widest field we can muster, but it has to be pin sharp from corner to corner. There's no point in having a wide field of view if your stars are slightly, or stars or galaxies are slightly distorted towards the edge of your field of view. So they wanted a field of view larger than 3 degrees, and that required a novel 3-mirror design. The primary mirror is about 8 meters in diameter, basically the largest mirror you can make in one piece. But the focal length, notice, is not that much bigger. The focal length is 10 meters, and that gives you an F number of an astounding 1.2. Remember the chart I had before with the Hubble and the ELT being F22 and F16, and most people's cameras would only go to F4, F2.8, F2 perhaps. This optical telescope works at F1.2, and it does that with a very unusual mirror. Let's just dim that out slightly. The light hits the main mirror and then bounces up to mirror number 2, and then comes down to hit mirror number 3, which is the same piece of glass as mirror 1. In other words, the mirror has been ground into 2 different shapes. That single piece of glass has been ground into one shape to act as mirror 1, and the center of it has been ground into a different shape to be mirror 3. And then from mirror 3, it bounces into the camera. This is how the mirror was made. You put lots of glass blocks down into a furnace mold, about 8 or so meters in diameter. You then melt it and spin the furnace. And if you spin the furnace, that means the surface adopts something close to a parabola, which means that's not the perfect shape, but it gives you a good starting point. It means you don't have to grind away 5 tons of glass before you're, roughly speaking, at the right shape. A camera that's looking into the furnace when the glass was melted shows you what happens. There's the glass melting and then sinks into the ribs in between the hexagonal regions there. Just repeated, it melts and then sinks into the rib structure behind. It melts and then sinks like honey into the rib structure to give you a very stiff mirror, even though it's not particularly heavy. That's it once it came out of the furnace and was cold enough to sit on. Apparently you have to sit on a mirror once it comes out, that's the law. So here, the various people that were involved in making the mirror, you can see the hexagonal structure of the ribs behind it. This is before it's been figured into these 2 rather odd shapes. But if you want to get a very wide angle, not only do you have to have a very novel way of getting the light over 3 degrees into your field of view, you have to make sure, of course, your detector is capable of recording all of that information. There's no point in having a very wide field of view if you've got a tiny detector which is not capable of recording all the information you need. So no, that's not it. That's just to give you an idea of scale. That's roughly speaking how large the mobile phone cameras are these days. They might have changed a little bit, but this is a standard module that you might find in your mobile phone. You can see that the glass and the chip behind it basically only a millimeter or 2 in size. For comparison, let me show you the size of the Hubble chip. This is the chip in the Hubble Space Telescope camera number 3, and that's its actual size, 4 centimeters by 4 centimeters. So that's what's given us all those fantastic images from the Hubble. 40 millimeters on a size, 16 megapixels in total. That's state of the art as far as the Hubble is concerned. What they've taken is a chip of the same specification, and let's just take that down a little bit. There's the 16 megapixel chip. Let's take that and add 8 neighbors of the same resolution. So now you have a whopping great detector. But that's not it. Let's just shrink that down so we can see it a little more clearly. There's the 9 detectors, each of which is equivalent to one of the detectors inside the Hubble Space Telescope. Let's take that little package of 9 and let's add another 8 of those to it. And then let's add another 12 of those to it. And then let's add a little bit of focusing and wavefront correction. And there we have the detector full of image sensors and guide sensors and wavefront sensors and a whopping 0.6 meter detector on a size. 3 gigapixels, more than 3 billion pixels. And if you're having difficulty working out what 0.6 meters looks like, that is a mock-up of the actual size of the detector. That is the detecting surface of the LSST. So it's looking at a 3-degree chunk of sky, and that's been imaged onto the 3 billion pixels that exist in the detector. Really going some. I cannot possibly show you what sort of images this is going to produce, because either my laptop or this projector is not capable of showing you 3.2 billion pixels in an image. So the only way I can see to actually give you an idea of what the LSST is going to produce is just to show you a very simple simulation. Let me not try and show you what the whole image is going to be. Let me show what you can expect to get in a 15-second exposure inside that black square there. A very, very small fraction of the whole thing. That might be expected to give an image akin to that. If you're looking at a nice dark sky with a 15-second exposure, you will pick up thousands of stars and thousands of galaxies. But remember, this is 1 part in, what is it, 3,000. The actual image is 3,000 times the area of what you're looking at the moment. And that is what can be caught in 15 seconds. So you can see that the total amount of information that is going to be gleaned by a series of exposures is absolutely vast. Remind you that the Hubble Space Telescope field of view, compared to the size of the moon, the Hubble Space Telescope, you've seen this sort of analogy before with the Hubble Deep Field, it's only a tiny, tiny fraction of the full moon. If we wanted to show the field of view of LSST as a large circle that encompasses that detector, we can't fit it on the screen. The best I can do is to show you the curve. If you can imagine the size of the circle, a little bit less than the size of this room, that would be the equivalent size compared to the Hubble Space Telescope. You can see the amount of sky that it can cover in 15 seconds is thousands of times more than the Hubble Space Telescope is able to deal with. It will be doing this at various wavelengths. It has a number of filters. The filters cover the visible part of the spectrum and also go a little way into the UV, and there are quite a few infrared filters. This will make it quite useful because remember, the most distant galaxies will be receding from us, in some cases at more than the speed of light, and therefore their light will be redshifted from possibly the UV or the visible, and probably be redshifted into the infrared. So having the capability of looking into the infrared is very valuable for seeing those most distant galaxies. Arguably, perhaps not so important. Same thing is done with this camera, except you can see the size of the filters by this rather decapitated individual in the right, who gives you a sense of scale. The camera itself is about the size of a small car, and these filters are basically circular filters, individually large enough, of course, to cover the entire detector, because they're up the close to the focal plane rather than further down in the optical system. How is LSST going to work? It's got a certain sky that it can see. It's in the southern hemisphere, so of course it can't see everything. It can't see all the way north, for instance. But of the sky that it can see, they have decided that they are going to visit each point in the sky a certain number of times, unless they find something interesting, in which case they could change their mind. So the colors here indicate how often that patch of sky is likely to be visited over a 10-year period. Most of the southern hemisphere is going to be visited something like a little less than 1,000 times during the 10-year lifetime of the project. South celestial pole will be visited a little less often, mainly because the quality is not quite so good because it's lower down, more air mass to image through. So they're going to concentrate on that part of the sky that is plenty high enough in altitude that can be seen clearly. It's also going to be, you see that there's a few odd little bits, like they're going to try and follow the galactic plane as far north as they can go before it's lost in the northern horizon, as seen from Chile. And they're also going to make an exception for the fact that they really want to cover the ecliptic. So not only the part of the ecliptic in the southern hemisphere, they're also going to monitor the northern part of the ecliptic and that part of sky to try and make sure they don't miss anything in the solar system. Yes, there's always the possibility that some objects could have very elliptical and very inclined orbits, and it might be that some of those objects are going to be up here and perhaps missed because they are simply not visible from Chile. But that notwithstanding, they are going to try and cover the entire ecliptical plane and also the galactic plane, and cover as much as possible of the southern hemisphere. There will be some particular objects, for instance, perhaps the Magellanic Clouds or other objects, which will warrant particular scrutiny, and there you can't see it in this particular image perhaps, but some of these are very dark blue, indicating they might well go back to this more often than average, and they might spend more than 1,000 visits to a particular object which might be quite interesting to them. So that's the sort of philosophy, which could change night on night, because it won't be an operator deciding which particular bit of sky they go to next. There will be a computer algorithm that decides the optimum movement of the telescope. Obviously, you want to minimize how much the telescope moves in between each bit of sky that it's going to look at. And you want to minimize how many times you change the filter. You don't want to keep changing the filter back and forth and back and forth. You would want to image one bit of sky with one filter and then perhaps decide to change the filter and image another chunk of sky, or perhaps re-image the same bit of sky. That will be decided by an algorithm that optimizes the whole process. What about the data it's going to be producing? The LSST is going to generate shed loads of data. How are they going to store it all? My guess would be, well, why not floppy disk? Okay, do you remember floppy disks? Yeah, you can remember these things. A megabyte. Yeah, I kid you not, you can store a megabyte on one of these things, more than 1 million bytes of information. But of course, that doesn't get you very far these days. Hands up all those who thought there would be zebras in this talk. No? Okay, right. There's a picture I took whilst I was on Safari a couple of years ago. That's a 2 megapixel reduction from the original raw image. Having reduced it down to 2 megapixels, it now takes up about half a megabyte. So I could fit a couple of those images on a floppy disk. So floppy disks, not much use for modern digital photography. But of course, you can always swap, if you so wish, to DVDs. DVDs will store many gigabytes of information, nominally more than 4 gigabytes of information. So that's enough for thousands of digital images. I could go on Safari quite happily and shoot all the pictures I wanted of animals, and it probably would come to a few gigabytes. So if I wanted to, I could store every picture I've taken from a Safari, I could store on perhaps 1 or 2 DVDs. So if I had access to dozens of DVDs or even hundreds of DVDs, that would be enough storage to keep me going with wildlife photography for probably all of my life and the rest of my long life to come. So that is a huge amount of information. But the LSST, if it decided to store on DVDs, would fill that up in about half an hour. So we need a different way of storing information. What about a terabyte disk? A terabyte is 1,000 gigabytes. A gigabyte is 1,000 megabytes. A megabyte is 1 million bytes. So now we're talking about 1 trillion bytes of information, 10 trillion bits of information. A terabyte disk is roughly equivalent to something like 200 DVDs. If we had plenty of terabyte disks, that's how much would be filled in one night's observing. 20 terabytes of information would be a good night's observing. Multiply that by the number of clear nights in a year, and in Chile, you would hope to get at least 300 clear nights a year, and then multiply by 10 if the project is lasting 10 years. And then, of course, you need some dark frames, some flat frames, some calibration frames, etc. By the time you're done, the total amount of storage required for this project is something of order 500,000 terabytes. Or if you prefer, 500 million gigabytes. It's a huge amount of information. That's an awful lot of disks. They won't necessarily be using terabyte-sized disks. Maybe they'll be using something larger. Maybe in a few years' time, we will have found better ways of storing information. But the bottom line is, once this project starts in a year or two's time, they are going to have to be prepared to store lots and lots of information. Every 30 seconds, remember, pictures are taken at 15-second exposures. They will take them in pairs. That's simply to compare one with the other to tell you whether, for instance, a cosmic ray happened to have gone through your detector when you took your image. Simply by comparing one with another, if they don't look the same, you've probably got a cosmic ray going through your detector. So they will always take them in pairs. And a pair of images, 15 seconds, so that's every 30 seconds, you will generate something of order 15 gigabytes of information. That information will then be squirted from the telescope down to the base of the mountain, which is the headquarters, if you like. So there's an intranet that gets you information from the telescope to HQ at the bottom of the mountain, so-called La Serena in Chile. That's a 100 gigabit per second optical fiber, so you can get your information from the telescope to HQ in about 1 second. Once it's in HQ, they want to send it to North America, and they can get it from South America to North America in 4 seconds. So 15 gigabytes of information goes from South America to North America in 4 seconds over the internet, rather than a dedicated intranet optical fiber. For those of you who can't get 40 gigabits per second out of your BT connection, a number of you may well have optical fibers now connected to your homes. It's getting more and more popular. Optical fiber can easily take 40 gigabits per second. That is not a problem for an optical fiber sending it via light rather than sending it by electrical signals. So what is stopping you getting 40 gigabits per second in your home? Well, what's stopping you getting it is the fact that the internet is absolutely chock full of YouTube videos, including this one probably. Now, most of the YouTube videos involve cats. And so if you simply put a cat filter on your internet connection from South America to North America, you can actually get something of order 40 gigabits per second. You simply have to control who's using it and stop all of the rubbish that normally gets pumped down the internet. So you put a cat filter on, and then you can get it from Chile to North America. And it goes to North America, to Champaign, Illinois, where they have a supercomputer center, the National Center for Supercomputer Applications, NCSA. That is the supercomputer base that does all the number crunching. They receive the images, hopefully no more than a few seconds after the telescope has taken them. And now the telescope might be moving to the next object, whilst the computers in North America are crunching on that 15 gigabytes of data, and comparing it with last night's or last week's or whenever that image was last taken. And it will flag anything interesting that has cropped up. Has any star moved? Has any new object been found? Has a star changed its color? Has it changed its brightness? Has it changed its position? Have we got a supernova going off? It will check pixel by pixel and flag anything interesting that's happened, and it should flag that within 1 minute. And then it will tell the world. So if you want to know, it will actually allow you to basically monitor things that have gone off and things that have changed on a timescale of almost seconds since they were actually acquired. So the supercomputers at NCSA will basically produce events. An event is something has happened, and it will produce probably about 10 million per night. So 10 million things have changed. 10 million objects have moved in the solar system, or stars have moved in the Milky Way, or stars have changed brightness, or supernova have gone off, or a new asteroid has been found. If you wish, they will send you a text message. Now, I don't suggest you sign up for all of them, otherwise you will get 10 million text messages per night. But for instance, if you're interested in supernova, then you might want to get this supernova has gone off as of 2 minutes ago, or this supernova has gone off as of 5 minutes ago. You should not be more than a minute or so out of date of whatever the telescope has been seeing. The intention is that scientists will be able to sign up for whichever particular type of event interests them most. So if they are interested in asteroids or new asteroids or asteroids that have moved in unusual orbits, they'll be able to sign up for, tell me when something interesting has happened with this asteroid or this type of asteroid, or tell me when a supernova has gone off in this type of galaxy. That's what these supercomputers will be responsible for, crunching every 30 seconds a new set of data that's coming in from the telescope. And in the process, it will build up the catalog of every object that is being seen. Obviously, on the first 3 nights observations, you can only image sort of less than half the sky, because you need to wait for a different time of year to see a different set of constellations. So it'll take a little bit of time to build up the catalog, but it'll only take 6 months or so before you've got tens of billions of stars and galaxies in the catalog. And then the catalog will simply be updated. This star has moved. This galaxy has changed its color. This particular object is now brighter or fainter than it used to be. It's not just a snapshot, remember, it's a time sequence of any of these billions of objects you're interested in. You will be able to get a time sequence of what it's been doing since the project began. there's bound to be an app for that. I'm not sure it exists yet, but as well as scientists signing up for tell me when this particular event has happened, there will also be an app such that you'll be able to look at what is the LSST doing at the moment? What did it do 5 minutes ago? What did it find tonight? Are there any particular objects that are worth me as an amateur going to have a look at? Because as of 10 minutes ago, the LSST apparently saw something interesting. Okay, there's always the chance that it looks further south than we can see from the UK. That would be a bit of a shame, but these apps will be available. So be careful what you sign up for to make sure you don't get too many pings in the middle of the night. So the LSST is on the horizon. It's been many years in the making. Many years in the design. The construction of the mirror was finished some years ago. The construction of the camera was finished relatively recently. Most of the construction on the top of the mountain is now basically there. And pandemic notwithstanding, hopefully it won't be too long before the first data starts rolling. I'm not sure what the current prediction is for first light. Addendum. I've been talking about the Large Synoptic Survey Telescope. Perhaps those of you in the know, those of you who read the magazines, realize that the name has changed. So it's been called the LSST for the past 10 years or so during the planning and the development and the ideas and finally the construction. So the LSST acronym is fairly well embedded in a lot of people's minds, and I still tend to use it, not least because it's a very descriptive acronym. It tells you what it is. It's large, it's synoptic, it's covering the whole sky, it's a survey telescope. But recently they decided that the observatory would change its name, and they changed the name of the observatory to the Vera C. Rubin Observatory in recognition of the contributions that Vera C. Rubin made in the study of dark matter back in the 1960s. The telescope itself is no longer called the LSST. The telescope has now been renamed the Chamonix Survey Telescope, named after the donors who've put quite a few $1 million of cash into the donation there. So the LSST is now the Chamonix Survey Telescope, not the Large Synoptic Survey Telescope. And because they were so wedded to the fact that LSST is in the public consciousness, and they'd already paid for the domain name lsst.org, they decided that the survey is going to be named the Legacy Survey of Space and Time. What's the acronym? Yeah, of course. So yes, LSST is still a valid way of referring to this survey. Technically, it's not the telescope anymore. It's the survey that the telescope will carry out. So Vera Rubin is the name of the observatory. Chamonix Survey Telescope is the name of the telescope, but LSST is still a valid way of referring to the project if you so wish. Still a bit of a tongue twister, but whether or not it's any better or worse than any other telescope that's out there, you can decide. So I've been telling you about why we have surveys in the first place, why we need a new survey, why we need a new telescope to make that survey, because no other telescope is capable of doing what the LSST will end up doing. I've said a little bit about the science, just touched upon some of the science, and a little bit about the technology that allows that science to be delivered. And then I finished with a little bit about how the data will be handled. So a couple of years ago, I gave you Fiat Lux and I demonstrated how we can measure the speed of light and the wavelength of light. And our knowledge of how light works, arguably how the universe works, and particularly how electromagnetic waves work, that allows us to decide how to build telescopes. And Fiat Lux II was talking about how we use that knowledge to design telescopes with lenses or with mirrors. And here in Fiat Lux 3, we've just said, let's look at one particular telescope and what it's able to do for us. It allows us to see the universe and hopefully allow us to get a better understanding of how the universe works. And ultimately, we end up with a cycle. So that brings the Fiat Lux trilogy to an end. Thank you all for listening. Do you want to say anything? Or you... Okay. Yes. Yeah. Tea break is fine. Yep. Tea break is fine.
Okay, we're going to take a tea break now, but we can't all go at once, I'm afraid. So we're going to do it in sections, about 8 or so, no more than about 8 to 10. out there at a time. When you get your cup of tea, you can come back in here again and sit socially distanced and have your cup of tea. So if you start from this side, about these first 2 rows perhaps just go, and then when you come back in, the next ones can go. Okay, thanks.
Can I just say that handouts are available from this web address, and I printed off a few.
This one since February 2020. So we need just the microphone, please. Restart. Okay, let me just check it's all on. And we'll hand over to Steve again. Yeah. Okay. There you go, sir.
Good evening, everybody. And at long last, we're able to say we have a new member. 18 months away, right? So if this gentleman could stand for one brief moment, it's Peter Nelson. Thank you very much. Thank you.
Hold on. We've got to do the right thing. So I'll let you do it.
I might do, yes. Forgotten what we say. Yes. Do we accept Peter as a member?
All those in favour?
Hold your hands. Anyone against?
Anybody object?
Well done. Well done.
Right. No. Welcome to the society. Well, welcome to the society.
I just want to add one more thing as well. A few people have asked me about subscriptions. What we've decided to do is to defer subscription or the taking thereof until the new year, at which point we'll make an announcement about what amount and what have you. Okay, right, thank you very much.
Thanks, Chris. Now we're going to hand over to Steve again, and we've got some questions. Questions from YouTube and any questions from the audience as well.
We're dealing with YouTube first, are we? Yep, that might be easier. Then we can take the room, perhaps. Will the data be made available to the public, I guess is the question. Yes, like many projects that are being funded these days, the data will be available. The catch being there is so much of the data, how on earth are you going to get your hands on it? Simply saying the data exists in Champaign, Illinois, come and get it if you wish, doesn't help if there's 500,000 terabytes of it. You'll need a fairly good internet connection. So anybody that wants to copy the data, and that means professionals, universities, or other data centers, might make copies of it, but at their own expense. In other words, they'd have to set up data servers and then copy the data from either South America or North America. So in principle, yes, the data is available, but the practicalities may make it very difficult for any individual to get their hands on that data. I believe there will be citizen science projects, but I'm not sure what they're going to look like just yet. Any other questions? Is that it from Zoom at the moment? Okay, from the room. Oh, yes. Yeah. For the benefit of the Zoomers, the question was, what's the implications for mega constellation satellites flying around the sky, mentioning no names? It's going to be a problem. The LSST is going to be covering the whole sky and cannot afford to simply point where the satellites aren't, because there are going to be so many of them. With Musk and Amazon and others effectively producing tens of thousands of satellites, it is going to be impossible to avoid them all. So almost certainly there will be wastage. There will be some frames that are taken which are almost unusable. And they are trying to find a mitigating strategy. They are trying to figure out how many satellites are going up, when are they going up, how bright are they going to be, are the people who are launching the satellites going to do their best to try and make them as faint as possible. The real problem is it's not simply a question of there will be multiple satellite tracks on each image. The problem will be that some satellites are so bright, they will effectively leave an afterglow such that the entire image is wasted, and possibly the next image after that will also have a ghost of where these tracks were. So it's not simply a question of saying, oh, there's some satellites there, let's take another 15-second exposure. It could be that it actually has a knock-on effect, and there will be so many tracks predicted that it will be an issue. LSST organizers are, I believe, talking to the people that are putting the satellites up, but the people putting the satellites up are not going to say, oh, I didn't realize that was a problem, in which case we're not going to put them up. They are still going to go ahead. They are still going to try and make profit out of launching those satellites. They say they are working with astronomers, but we are yet to see any solutions to the problem. Yes, sir. Yes, it'll have a resolution which is probably sub-arc second, but it's not going to have the resolution of, for instance, milli-arc seconds, which is something that you might be able to obtain with Gaia or the Hubble Space Telescope. But if you want to monitor what's out there and you want to see stars moving or asteroids or trans-Neptunian objects, then sub-arc second accuracy is basically all you need. You can still catalog 30 billion objects with sub-arc second resolution. You can't do that with milli-arc second resolution, because if you design an instrument with that resolution, you don't get the wide, fast, deep response that you need for a survey instrument. So survey instruments, in a sense, are incompatible . Yes. Are we likely to pick up large scale objects rather than tiny objects at the level of fractions of a degree? Or are we possibly going to pick up objects that actually occupy a huge chunk of sky that we can't normally access? The answer is probably yes, as long as they are bright enough. And by bright, I didn't mention this earlier, but somebody put me up on it, was to give an indication of the magnitude limit that the LSST can go down to. Gaia can image stars down to about the 20th magnitude. The LSST should be able to go down 5 or 6 or 7 magnitudes below that. So the limit will be something like the 27th magnitude. So if there are objects out there, whether they be diffuse gaseous nebulae or other objects, if they have a brightness above the sky that gives you the ability to see contrast, then in principle, they will be there in the data. Yes, in the sense that if these clouds are, for instance, let's say there was a giant molecular cloud which was low density, so is not obvious, but was moving through the galaxy, then whenever it happened to pass in front of more distant stars, those stars would dim slightly, and that would show up in the variations. And one of the things they're going to do is to try and mine the data with artificial intelligence to look for patterns, not simply star number 1 has got a bit brighter and star number 2785 has got a bit dimmer, but to actually look for patterns that could be, there's a particular thing happening over here. These stars seem to be changing their brightness in a correlated way. Something must be passing in front of them, or they are gravitationally bound to each other. So yes, artificial intelligence will be used to try and find patterns that would otherwise have been missed completely. Yeah. Yes, sir. Yep. I think they may have to if they continue to have these problems with satellites producing ghost images. That was not part of the original design, I think, when they first thought about this, but it might be one of the mitigating strategies. Sorry, I didn't repeat the question there. The question was, is it possible to pre-flash the CCD to effectively wipe it such that you don't get a ghost image from the previous exposure? And I think the answer is they hadn't planned to do that, but they might have to, if that's the only way of dealing with lots of satellite trails. The problem being that even if you do that, you might get rid of the ghosting from one frame to the next, but you still have satellite trails on each frame. So it may not be the solution they're looking for. Yes, yeah. They want to be able to move in only a few seconds. The telescope is designed to be very rigid so it can move very quickly to the next patch of sky. And the computer that decides which patch of sky it's going to look at next will make sure that it doesn't have to swing to a completely different region of the sky and come backwards and forwards. It'll try and minimize how much the telescope moves between each pair of images. Remember, it takes a 15-second and then another 15-second exposure, and then it will decide whether it's going to take a few more seconds to move the telescope and which way, etc. And yes, if they want to continue taking data at the rate they want to take data, they can't afford to waste even a few seconds. That will add another 10%, another 20% to the length of time it takes them to collect all the data they want to collect. And the scientists are assuming that data will come off the mill effectively every 30 seconds, or a little bit slower than that, but certainly a pair of images no more than once a minute, no less than once a minute. Yes, sir. Yes, the question is exoplanet atmospheres. Yes, survey instruments are not optimized for that sort of thing. They will find exoplanets by accident because they're looking at star brightnesses repeatedly, and they will notice if stars change their brightness in an anomalous way. But yes, if you want to see the atmosphere of an exoplanet, you get a very high resolution instrument like the Hubble Space Telescope, and you get its spectrometers on it. You don't take images at different wavelengths, you get a spectrometer and you get the spectrum, and then you look for the signs of water in the atmosphere or whatever. Hubble is exceptionally good at doing that. It is not what you would do with a survey instrument. Yeah. 2 went up there, yes? Let me remind myself that the question was, what are you going to do about all of the new objects that are found? The Minor Planet Center normally ratifies any new minor planets or asteroids that are found, but there's going to have to be a way of dealing with it automated. It will probably, again, be artificial intelligence that sifts through all the data, picks out the new objects that weren't previously known about, and will automatically catalog them into a database. There was another question there. That's a very good question. Are there any plans to do the same in the Northern Hemisphere? Not as far as I know. So the intention is that if you can cover the ecliptic, you've got the solar system covered. If you can cover half the galaxy, you've got most of the Milky Way covered, including the halo of the Milky Way. And as far as the universe is concerned, it doesn't matter whether you look that way or whether you look that way, if you want to get the large scale structure of the universe. So there are clearly some advantages in going and building a duplicate in the Northern Hemisphere, but that would be a very expensive thing to do for a relatively marginal improvement on the all sky coverage. So as far as I know, that's too expensive to consider doing that. Yep. Who gets the credit for the new discoveries? I think it's like pan-stars. How many comets have been called pan-stars or things like that? It's yes, it will probably be catalogued as a new discovery, and it will probably be catalogued as LSST number 1, 2, 3, 4, 5, 6, etc. So I don't think we'll ever be in the position of having some individual. It might change with citizen science. It might be that somebody sees something in the data that the artificial intelligence trawling has missed, and somebody looks at an image and says that's odd, and it might be that they then get credit for that. But it is so much of this is going to have to be automated, at least in the first sift, because if you imagine just a single image of 3 billion pixels, it'll take you a while. I mean, how many monitors would you need in order to display a 3 billion pixel? I think somebody calculated it would take 1,000 high definition monitors just to display a single image that comes off. So the idea of somebody sitting and looking at it is not quite what's going to happen. At the very least, something is going to do the initial sift and then highlight something is odd about this, something is weird about that, and then perhaps people will actually look at them. Basically, the LSST will provide the data, and what's hoped is that not only will that identify objects in which you can then say, let's go and have a look more closely at this object with this telescope. The idea is it will produce a database which all scientists will have access to. So if a scientist who's interested in dark matter wants to check whether or not the dark matter distribution around galaxy looks like this, because that's what he believes his theory is telling him, he will be able to go to this repository of data generated by the LSST and then see if what the LSST is seeing agrees with his simulations or his models, for instance. So it'll always be in collaboration with theorists saying, we would expect to see this, this is the data we actually get, and do they tally? In much the same way, how do we know the Big Bang happened? The simulations tell us the Big Bang happened and then these structures formed. We look into the universe and say, are those structures the same as the ones we see? That tells us the simulations are either good or bad or need tweaking. So it's always, here's the data that will then inform the theorists who will then use that data to either verify or break down their ideas, their models, their theories. If it exists, if it exists, it will be found. That's the bottom line. So, Gerard had his hand up there. Any day now. Yeah, yeah. So the question was, can you launch multiple James Webb Space Telescopes and then link them together to get effectively an interferometer of space telescopes? Space telescopes are complicated enough in the first place that I think that extra complication is probably a little bit too far for the moment. I think you could arguably do more by doing adaptive optics with ground-based telescopes, which is a lot cheaper. Let's face it, how much has the James Webb taken? Partly because of the length of time it's taken, but just like the Hubble Space Telescope, it is many, many billions of dollars that are put into getting space telescopes to work. So the last thing you need is another element of complication. So I can't see that happening in the near future. That doesn't stop it happening in the more distant future. If we're talking about having gravitational wave interferometers in space, then there's no reason in principle why you don't have the same sort of cooperation between individual imaging telescopes, but the benefit there is less obvious.
What a really, really appropriate title for our first in-person lecture after kind of 18 months of darkness and isolation, really. So it's very, very appropriate indeed. We went to visit Greenwich Observatory a few years ago now, and it was John Flamsteed's life work was cataloguing thousands of kind of objects, and to think that we're now looking at cataloguing or surveying billions is absolutely mind-blowing, and I think it's really quite amazing. And I'm really looking forward to seeing some of the answers to some of the questions that we've all had. Really excited about the dark energy. That'd be great. And as a Star Trek fan, we might even find mushroom kind of sequences to, you know, to enable a warp speed, but you never know. Okay, and a really, really cute cat. So the obligatory cat. I'm also fascinated by one of the things that's really taken off in lockdown was the use of things like Zoom, etc., and the use of apps and how dependent we've become. So it'd be really interesting to download the app and be able to at least kind of presumably get some sort of highlights of what's discovered in kind of real time. So on behalf of the membership, I would like you to join me in our time-honoured way of saying thank you to Steve for the round of applause. So thank you very much.
Thank you very much. Britney Spears never has this problem. Okay, folks, thank you very much for coming along. That was it's fantastic to see so many of you come here. Oh, sorry. Okay, yeah, okay. All right, let me just say what the date of the next meeting is. Then I'll hand over to Dave, because I think if you want to hear about PEXIL, it's important that Dave gets a chance. The date of the next monthly meeting will be in here, all things being well, when we will have members' short talks and papers. If anybody would like to give a talk, a 15-20-minute talk on any subject, well, any astronomical subject, then please contact Mark or myself. So I'll just say thank you very much and take care on your way home. But I'm going to hand over to... Oh, did I not give a date? Well, I'm not telling you. Okay, so Friday, December the 10th, 2021 at 7 p.m. Thank you very much. I'm going to hand over to Dave now, who's got some information about PEXIL. Thanks.
This is not like Zoom, is it? Right. My apologies for my lateness. Sorry, very sorry, Steve. I had a retirement due. My boss retired. I've known him for 40 years. Couldn't get out of it, and I ended up in the pub with him there. And there's only... That's okay. Hi everyone on YouTube. Basically, there was like 2 of us left in the room while he's waiting for his lift back home. We couldn't just leave him on his own. So my apologies. Nice to see everybody in the real world for a change, and I realise now you're all not little boxes, which is great. Yeah, but PEXIL, it's been on the scenes for the last 18 months, is it thereabouts? We've still been busy as councillors. All our council members here know, been very busy in the background, keeping things ticking away as the best that we've done. PEXIL has been interesting. I'll come to Flygate in a moment. First of all, United Utilities decided that they needed to put additional lighting up at the adjacent building where for those who know, the pump station at the back of the observatory, that basically is providing water to the new project that's getting built down by the motorway. So a big thing going on. They didn't consult us at the observatory, but we found out through the grapevine, as you do. Someone brought it to the attention, contacted them, and they said, oh, what can we do to help or to improve the situation? And we explained the environment. We have a bat population as well, which we, of those Wednesday regulars, we see the bats flying around. So it's lovely to see. At the same time as all the wildlife in the area, the bird population and so on. And it's all affected by, as you know, light pollution. And in particular, these LED lights are full spectrum. They can be very, very bright and rooms are dark adaptation straight away. My concern was that how high the lights were going to be. with consultation, we managed to get the lights, keep them down at the ground level. They are white light, but not the LED, which that's good. And they've basically got them on timer. So as the engineer walks around on those hopefully rare occasions where maintenance is required, the lights will just come on and go off as they walk around the area. We've been up in the dome looking down on where it's lit up, and it doesn't seem to hinder the observation up in the dome area. So I think we're going to be okay. We've only got till March to basically assess the situation. We can have things improved if that's the case. After March, we've got to go through the channels, unfortunately, but I think we're going to be okay on that. That's basically the biggest thing that was going on. Was light pollution and the problem that it would give us, and probably ruin it as an observatory. It would just be a meeting room. So I think we're actually doing okay up there. I'm going to. We've got to put the humorous side to this, Chris, haven't we? Myself and Noel Rimmer, were taking books up to the observatory on those rare occasions that we actually went up there. We opened the door to the lower observatory room, and basically there was literally 1,000+ flies in there. The observatory windows upstairs, downstairs, all of the rear of the observatory had been smashed by vandals. That was bad enough. They didn't gain entrance into the building, so that was a blessing. But the problem then was that all the windows were wide open to the atmospherics. We think flies come in, or some flies have come in, or something's come in and basically died. The flies have laid eggs. Basically, you get the cycle where you get your maggots, and then from the maggots you get your flies, and it was a cloud of flies. There is anybody wishes to see the video, it is there. What you don't get on the video is the sound. There was no smell. There's no rotten flesh smell, so we don't know what was the origin of it. No skeleton. So basically, Noel had to go. He had a meeting somewhere else. Chris had come up unbeknown this was going on, and basically I just said, you said, are we going upstairs? So, yeah, we'll go upstairs. I said, how are you with flies? Are you queasy? Oh, I'm okay, Right, okay. I didn't tell him there's like how many there were. We went up, but me and Noel prior to that sprayed the room with fly spray. I shot out and got some fly spray, one thing or another. That killed some. Okay. 4 cans of fly spray, yeah. And basically we just closed the door behind us. So when Chris came up, those flies there was less than 1,000. There's probably only 800 at that point, and they were all dead on the floor. They remained there. So then Chris and myself carried on, and we just blitzed the place. It was what can we do? Is it's a bit of a dilemma. We can't just leave it. The windows are wide open to the to the outside. So basically, it was a case of just fly spray everywhere, wasn't it? Close the door, come back in 20 minutes, it depleted, come back in another 20 minutes, do the same again. Eventually, we got it down to maybe 3 flies, and they were the tough ones. They were scouse flies. Yeah. Of course, yeah, I apologize. Yeah, up to that point, the windows had actually been boarded up since they were smashed, but that led to the problem that nothing could get out the windows. So we had to work out a routine. So we had windows open on the corridor. So the door was open, flies flew out. We closed the door, opened the windows, and there was this progress of getting rid of the flies. We got it down to 0. Since then, we've been up and things have improved. You did go last week and there was ladybirds in, wasn't there? Yeah, a couple of ladybirds, but it looked okay. So that's what's been going on in the background. It's been fun. It really has. Hopefully we never have to deal with that again. The consequences of the broken windows, the conservation group that work up there, they're pushing United Utilities at the moment to have the windows replaced, and United Utilities are going to do that at their cost. They've also discussed putting shutters on the outside that are motor driven. I like the idea of the motorized. I think about an observatory. That would be good. Basically, open it from the inside with a key, and the motor will open the shutters and close them. That hopefully will be done at their cost, not ours. Winter's coming in. That's the concern. They've got the heating on. It's going literally out the frames and heating the atmosphere up. So they're pushing on that, and hopefully, come the coming weeks, we'll have that all sorted. Basically it really. Donation of library books. We've got over 100 more books. I think we're just going to have a Pexel library at some point. One donation. Yeah. Some good stuff. Yeah. But hopefully we'll, yeah. Yeah. What we usually do when we have duplicates, we will take the better quality and keep that on the shelf for the society itself, and duplicates would then be sold on to the members at a good price, I think, reasonable price. So that's it, basically. Everyone's supporting in the background. Council really appreciates it. It's not been the best of 18 months, has it, really? But we're all still here and the society's still going, which is always pleasing to see, Steve. Thank you very much.
Thank you, Dave. Okay, guys and girls, meeting closed. Thank you ever so much for coming along. We would appreciate feedback. Tell us how it went for you. Tell us what you thought of the COVID rules, whether they were too much, whether they were not enough. You know, we'd like some feedback. So it would be good to, if you can reply to the email that Mark sent out. Oh, actually, I sent it out. Reply to the email that I sent out. Then we'd like to get some feedback as to what you thought of tonight. Okay, and we'll, if we need to, we can just change things a little bit for the next one. Thanks a lot. Safe journey home. Thank you. Bye-bye.